Good evening. Tonight we're going to start looking at equilibrium. So when we think of equilibrium, we think of things that are equal. Well, what we're going to look at is that is equal are chemical reactions, our forward reaction combined with our reverse reaction. Well, we haven't thought of things that way before. We just think of them in one direction. We have reactants, they do some kind of reacting, and we produce some kind of product. Well, this doesn't just go in that direction. In some reactions, once you have enough of that product formed, what we're going to find is they will start reforming and they're going to turn back into our reactants. When this happens, we get something known as a reversible reaction. This is defined as a chemical reaction in which the products can react to reform the reactants. So let's look at an example of what I'm talking about here. If I take some mercury oxide and I decompose it, let's say it's in the solid state, I can get some mercury. Mercury comes in the liquid state, and oxygen, which we know is usually in the gaseous state. So that's the typical reaction, decomposition of our mercury oxide. However, once I get enough of this product, I'm going to see that they begin to again synthesize. So our mercury gets added to our oxygen gas and it reforms our mercury oxide. Well, if we had to write both reactions every time, it would get kind of long and, kind of redundant. Just like those Lewis structures where you hated writing all of the different resonance structures. Well, to simplify this, instead of writing both, what we can do is use a double arrow. So we could take our original reaction here, and instead of writing one arrow, we're going to write two arrows. So one going in the forward direction, one going in the reverse direction. This double arrow then is going to show someone looking at the reaction that this is a reversible reaction. It can go in the forward direction or it can go in the reverse direction. Now these usually happen at the same time. Of course, you're going to start with the forward reaction more, and that's going to occur at a much faster rate because you have more of that product or more of that reactant to begin with. But once you get that product, then you're going to start seeing that reverse reaction start to occur. Eventually, this all starts to even out and we get something called chemical equilibrium. In chemical equilibrium, our rate of our forward reaction is going to equal the rate of the reverse reaction. And your concentrations of your reactants and products remains unchanged. So if you think back to the lab that you just did, you saw that it didn't start out equal, but eventually, even though the amounts weren't the same that you were transferring back and forth, you finally did hit an equilibrium in which these reactions or the rates were the same and the concentrations that were switching back and forth remained unchanged. Well, let's look at a general, very general, as you can see, type of an example. So in this example, our first letters are going to be our coefficients. So these are just going to be our coefficients, as if we balanced our equation. The second letter then here are going to be our substance. So remember, we always start with our reactants and we end with products. So when we begin this, initially, A and B are going to be at their max concentration and C and D are going to be at 0. Just like your graduated cylinders, you started with the first one at the max 50 and the second one at 0. As your lab proceeds, though, A and B start to decrease, and C and D will start to increase. And we have reached equilibrium when no more changes occur to the concentrations of either side. So not necessarily your amount, but your concentration doesn't change back and forth anymore. We're not seeing any more happen. So if we looked at this more as a picture, we can look at rates compared to time or concentrations compared to time. So you could see in your rate, your forward rate starts off really fast, but then it eventually slows down. Just like the reverse is going to start out really slow because there's nothing there to begin with, but then as we're getting more and more product, it's going to increase. Eventually that rate will equal out. So if you look at rate versus time, as they both come to an equality here, you have reached equilibrium. In the second one, you have your concentration and time. So again, your concentration at the beginning, your reactants, you have a lot of them, products, you don't have any. But as reactants start to change, they're going to decrease, and you're not going to have as many. Products, on the other hand, will increase, and you will have more of them. But as your concentrations again level out, we have reached equilibrium. So you're going to look for, in graphs, a leveling out, and that's what you should have seen in the graphs that you did in the lab. Now an easy way to kind of look at these, more than just graphing them every time, is to use some math. Yes, everyone's favorite. Okay, maybe some of you like the math, some of you go, oh, we got some math. Well, yes, equilibrium even has math. So we're going to look at equilibrium more as a math concept, and when we do that, we often get constants. In this case, we get the equilibrium constant. This is going to be based on the concentration ratio of products to reactants at equilibrium. So now maybe we need to think back and remember concentration. We are going to focus on our capital M, or our molarity. And remember, capital M is moles of solute over liters of solution. So when using our equilibrium constant, we get the equilibrium expression, and this is how we're going to calculate this equilibrium constant, K. So our equation is K equals C to the X times D to the Y all over A to the N, B to the M. So this is going back to that original equation, or that very generic one I had a couple slides back. Your brackets just represent concentration, and that concentration, again, remember, is molarity. And your superscripts you see there, the X, Y, N, and M, are your coefficients from that balanced equation. What we find is when we calculate that value of K, if it is small, the reactants are favored. So your forward reaction occurs slightly before equilibrium is reached. If your K is large, your products are going to be favored. So your reactants are largely converted to products before equilibrium is reached. So a small K, you hit equilibrium quickly. Large K, it's going to take a lot more of that reaction to go before you're going to hit equilibrium. One thing you will find, though, is that K, or this equilibrium constant, is dependent on temperature. So in problems, as you start working with them, they'll often give you a temperature. And that's because you change the temperature, especially when working with gases. We know that you can really change how gases react. Another thing you're going to look for are pure solids and liquids. These are not included in the equilibrium expression, or when you're trying to calculate K. So your concentrations won't change for those substances in the solid and liquid. Now, if you would like to look at some examples, you can watch the next video in which I have done some examples. If not, we will see you in class and we will work on plenty there. Have a good night.